Thank you, Brian. Next up, we have Lou Perazzoli to talk about memory management. If you've ever wondered about memory map files, he's the guy to ask.
The same file.
Let's just rip right into what's going. Okay, memory manager from the file system. What's it do? How's it fit? What's it control? This is really easy. It provides the underlying support for the cache manager. Okay, so the cache manager relies on the memory manager for all the virtual operations. Okay, so the cache manager says, gee, I really wish I had this file mapped into the system cache. The memory manager goes out and says, sure, I can map a view into this file. It maps it in 256 KB slots. So it's up to the cache manager to manage those 256 KB slots. So that's reserved virtual address range. That's a system virtual address, which means it's valid no matter what process you're running in. Okay, the cool thing is, in the fast I/O path, you can just copy out of the cache into the user's buffer. Okay, that's really neat. The other thing it provides is the management utilities for controlling this system cache. The downside is it's also a pain in the rear for the file systems. And the reason being is it uses the file systems to do paging I/O, which means you may be asking the memory manager to do one thing while it turns around and asks you to do something totally different that you really don't want to do, and yet the memory manager has this bad effect of not being patient. So, and an even worse effect is when it can't get through one way, it tries another. Okay, and you can see that effect as we start running out of memory. We start writing dirty pages as fast as we possibly can, and we start making the system cache smaller, which as a result of creating more dirty pages, which we try to write as fast as we can. So you can get into this feedback loop that just spirals your system down the toilet. The file system's job is to prevent that from happening, and they have a whole set of rules that they follow. If you follow the rules, we don't get into trouble, but when you don't follow the rules, it looks like the memory manager's misbehaving when it's really the file system's not cooperating. So some of the roles that the memory manager takes is it supports the system cache. It in-pages code and data from paging files. And you say, well, how did code and data get into the paging file? Well, the easiest way code gets there is I put a breakpoint in it. And now I don't want to write that breakpoint back to the image because we, of course, don't want other people hitting that breakpoint just because they ran Excel. And so when it gets thrown out of memory, it goes to the paging file. We also get code and data from map files, and we'll spend some time talking about that. And then, as I said, we write dirty pages to both of those files. As I'm sure you learned from your cache manager talk, we have a 64 to 512 megabyte process-wide range of address space reserved for this. We manage, I have an old copy of the slide, so I want to make sure I'm not off the slide or something. We manage the cache in the same manager as any other process. We grow and shrink the working set. And then we provide some really cute routines to the to the cache manager so he can do read ahead. He can check to see if I touch this virtual address in the cache, would I take page fault? Or is the page already in memory? So the cache manager can do some really clever things to know whether he's going to have to take a page fault. And if he is, he can set the read ahead up or down to service that request. And if you do the Win32 open call and you set the bit saying I'm going to do sequential I/O, the cache manager takes advantage of that by doing large amounts of read ahead because he knows you're accessing the file sequentially. And then the other thing we provide is for the backside for the cache managers to flush dirty pages and mark pages as dirty, even though the memory manager doesn't think they are dirty. And there's cases for doing that, for making sure the file systems get checkpointed and the data actually gets written out. And then the lock pages, so the memory manager won't ever write those pages out. And this allows our file systems like NTFS to have a careful write strategy such that no matter when the disk fails, the file system integrity is always kept because we write the structure changes before we write the data. Okay, what's sort of the downside for the file systems is pages can be written at any time, and we can do it asynchronously. The modified page writer is actually 2 system threads that sit there running at high priority time, 17 and 18, I believe, which is real time. And they're event driven. So that means that as we take page faults, we look to see how many dirty pages there are every time we take a page fault. And when we see too many dirty pages, we just set an event and tell this one of these system threads, the main one, to go write some modified pages. And it goes through all the modified pages and tries to gather large clumps together. We like to do I/O in 16 pages at a time, which is 64K on an x86 and 128K on an alpha. The reason we want to write large I/Os is obviously the disk gets quicker, over the network it's much quicker, and we minimize the latency going to the disk. We want to do this asynchronously, so while we're doing one write and we're waiting for that transfer to occur, we can be gathering up the next set of pages. And the reason we have 2 threads is because one of the rules that you'll hear about is you can't block writes to the paging file, but you might block writes to a map file. So one thread is dedicated to doing write to a map file because we don't trust the file systems, and the other thread's dedicated to gathering these pages up and then issuing the asynchronous I/Os to the paging file, knowing they can't block. Okay, because if you block a write to the paging file, everything gets very upset, as you can imagine. Because if you block a write, you're probably going to block a read. And if you block reads, that means people aren't going to make any progress, and the system does not run well. The file system has to obey the rules. And something that we just added in Daytona is the memory manager actually has some routines that it calls get file system resources. And we'll talk about those 2 places. Now, the other good news is David Goebel's going to talk this afternoon, and he's going to tie all this together. How the cache manager, the file system, memory manager all operate coherently to make things work. But just to look at how this very small view of the structures, oops, get back here. The key piece that you get to see is the file object. And what happens is the memory manager references that file object. And this is where life gets really bad, because this means you no longer have control of when that file object is going away. The memory manager doesn't have control when it goes away, but it at least has control how long it stays, so how long he has access to it. And so what happens is when you map a view of the file, and this could be through the system cache, the memory manager ups the ref count of this file through the object manager, and it squirrels away a pointer to that file object. And then there's 3 fields in the file object. I think in the structure defined as the section object pointer. 2 of those are for the memory manager and 1's for the cache manager. One of them is where we map files that are mapped as data. The other pointer points to some structures the memory manager uses when the file is mapped as code. They're different mappings. We'll talk about that. And the 3rd is used for the cache manager to find its structures, its VCBs and CCBs. The interesting thing is the same file, like an Excel.exe, could be mapped 2 different ways. One is data, one is code. Data is just laid out in nice page size increments, sequentially through the file. Code is laid out in an unusual way because of the way the linker does it. You might have 512K of code, and then you might have a 512, or let's say a 4K section of read-write data. Well, those have to be in separate pages, but they're dense in the file. So when you page fault in the code, we'll read 512 bytes into a page. And then when you page fault in the data, we'll go to that next 4K and read that in. But that's not 4K offset in the file, if you understand what I'm saying. So there's a different mapping between code or images and what it looks like on the disk, and data, what it looks like on the disk. And the memory manager maintains those 2 things to the bane of a file system, because it means you could have double references on the same files, code and data. And the data, to make it even worse, could be in a cache. Because the data could be in the system cache, but we'll never let the code reside in the system cache, because it makes absolutely no sense when you think about it. Because all code is never read into memory, it's always faulted in. If you're reading it in, it's a different path. It's not that, we're not executing it as code. Okay, so this is sort of the nasty structure that we build, which is everybody's pointing this way at each other, and it can't go down until everybody wants to cooperate. Oops. So how does the file object get dereferenced? When there's no map views, that's in the system cache or the user's map views. And now's a great time to talk about how map views are used and why they're good and bad. A user can do something very nasty. A user can open a file, map a view of that file into a different process, close that handle, and exit his process. There is no open file handle. The only thing that's keeping something around is that reference that memory management made to that file. And what happens is when that file is mapped, it's got some address range. So let's say he mapped a 1 megabyte file into another process and then snuck away. That 1 megabyte file is there. Anytime the user accesses it and it's not in memory, we're just going to do an I/O page read to bring it in through the pager. That's the same mechanism we use to bring data into the system cache. In fact, the page fault mechanism takes a trap, goes into kernel mode, gets dispatched, goes to the pager. In the system cache, when the data's not there, we check to see if the data's there, and then we call the pager directly so we don't take that trap. There's a bit of overhead associated with the trap, and it's actually quicker because of the way the cache manager calls us to just call the pager and not build a trap frame. That's the only difference. When we actually issue the I/O, it comes into the file system it comes into the I/O system in the file system the exact same way. It's an I/O page read request. It's synchronous, and we're going to wait for the return. Okay, so once a user maps a view, we're going to read to it, and then the only way that writes happen is either the user calls the flush virtual memory call, or the modified page writer decides it needs room and it writes out those pages and it does it asynchronously. Now, sort of the bad news for the users is the file systems, as Brian pointed out, honor lock requests. So the user can get some interesting errors returned to them, and the errors are returned as exceptions. Because the memory manager, when you take a page fault, there's no status that can be returned, so an exception gets raised. And the really unusual one that really baffles users is some guy has a lock, not an op lock, but just a regular lock, file range locking on a file. You take a page fault, and the memory manager does an I/O page read, and the file system comes back and says, that page is locked, that range of the file is locked, so you get an error back, and we can't return that to the user, so we raise an in-page error. And then the status code is file locked. And the user has to have an exception handler to handle that and deal with it. So you can get some very interesting things when people try to use files as memory map files and then use regular file operations at the same time. And everything's handled right from the system's point of view, but from the user, it may be very confusing. Why did I get this exception raised on this file I had mapped? But if you do your file system right, it's not a problem for you. It's just the user's not doing things right, because he should not be using locks and memory map files at the same time. They should be using locks consistently. So they should have done the read to the file system, not to the paging I/O. Okay, so the file object is going to be dereferenced when there's no map views, when there's no section objects. A section object is what happens when you call create file mapping. You get a handle back to a section, which you can then map if you so desire. So if the user doesn't close that section object, we're going to keep that file object referenced. And then lastly, as long as there's a physical page in memory, it doesn't even have to be in the system cache or the user's process. The user's process could be gone. It might not be mapped in the system cache. There's no handles. There's no user map views. There's no system map views. There's no reason for this file to stay open except there's a data page still in memory. We'll keep that open. And the reason we do that, obviously, is let's assume it's Excel. The guy ran Excel. He leaves. He comes back and says, geez, I want to run Excel again. And we bring it up and we say, oh, lo and behold, all of Excel's still in memory. So we don't have to go to the disk. And by keeping that file open, you can imagine how much faster that is than having to go to the file system, say, find this file, open it, go read some pages from the disk, and then fault all 4 megabytes of Excel back into memory. So that's actually a big win, and that's how, even though we're not in the system cache per se, we're still caching. And that's one of the things the memory manager does for the cache and the file systems, is it maintains pages in memory even when there's no demand for physical memory. Okay, so one of the ways the file systems can help close this file is there's 3 calls they can make. One is called purge section, which you're going to use for when you truncate a file, and it says throw the data from this file out of memory and reset it back to its initial state. So it just sort of points to where in the file that data would normally come from. The other is flush image section, which says, hey, you may have, remember we talked about the 2 pointers in the file object, 1 to data, 1 to the cache, and 3 pointers to the cache, and then 1 to the code when it's mapped as an executable. The file system has no idea whether it's mapped as data or as an executable. It may know that it's mapped as data, but it doesn't know it's mapped as an executable. So it calls this flush image section to say, if it was mapped as an executable, and the only reason you have data in memory is because it's sort of left over, flush it. And this is the case where I'm copying a new Excel over to my system, and I got Excel in the cache. I don't want it in the cache anymore. I want it thrown out of memory, so I put the new one in. Now, flush image section can return false, which says, hey, somebody's running Excel. You can't copy a new Excel to the system while I'm running Excel. And you have to honor that. If it says false, you don't get to go. The pages are going to stay there, and the file system handle is not to be closed. And the last is for section close, which says, I want you to do everything possible to get rid of all these pages for this file out of memory. And one of the other things you can set is you can say, even if you can't do it now, do it as soon as you can. So asynchronously, whatever's, maybe there's a user map view or whatever, we remember that. As soon as that view goes away, boom, all those pages will get flushed, and now the dereference will occur. Okay, so even though you can't get it to happen right that instant, you can get it to happen soon enough in the past. So we put this in for redirectors that really got to get rid of data, but the user's got data locked up in user map file, and there's nothing the redirector can do. But this way, as soon as it gets closed, all that data gets flushed. So the right thing happens. Okay, oops, one day. There's 7 rules that if you follow these 7 rules, everything will be coherent. Coherent is the key word. You have to make sure that the system cache, what's in memory in these sort of hidden cached pages, and what's on the disk is coherent. Okay, so the worst thing that could possibly happen is a user map view and a guy doing I/O get out of sync, and one person has a different view of what's in the file than the other person does, because then you're going to have timing related things like, does the file system do the flush, or does modified page writer do the write, determine what's really in your file, and that's bad. You want the file data to always be coherent. Okay, and if you follow these rules, it can never be uncoherent. So the first read is what pretty obvious. If you do a page read from the paging file, you can't take page fault. And when you think about that, it makes sense. The second rule is don't block when you're doing page reads. And some of the corollaries is you obviously can't page any code, you can't page any data structures, and you can't call anything that's not safe to call at DPC level, or I guess dispatch level, we call that. So essentially, you're pretty well bound up as to what you can do on that path. Page writes to the paging file sort of have the same rule. You can't take a page fault. When we're doing writes, we're trying to clean out memory, and if you start paging more stuff in, it sort of works against us. The other thing that you see happening is there may be 0 pages free, and so we can't complete the page fault. Everybody is blocked trying to do page reads, and we're trying to write pages, and we just get headlocked immediately. And paging writes should never block in the file system. There's some corollaries that writes can be synchronous or asynchronous to the paging file. Multiple writes can be outstanding at one time. And if you block the modified page writer, obviously the system performance suffers. Rule number 3 is real nasty. Paging files can be extended and truncated while writes are in progress. Okay, because remember, there's a couple system threads doing these writes. And then there's another part of the system which is taking page faults or whatever. And some user calls create virtual memory, and he wants to create, let's say, 50 megabytes of virtual memory, committed, of course. And we say, oh, the paging file is only 20 meg, but you said it could grow to 100 meg. So he needs another 50 meg, let's grow up by 50 meg. So we call the file system and say, please extend the paging file. Of course, the file system is going to stand on its head to do this. Why? Because the structures that manage the paging file cannot be paged, right? Because that would violate rule number 1, which says you can't take a page fault. So if I say, go write this page to the paging file, by the way, it's offset 40.2 megabytes into the file, you can't find that, those retrieval pointers where you go look that up have to be resident. You can't take a page fault on those retrieval pointers. So anytime you get one of these IRPs to extend the paging file, it definitely identifies it as paging file. And you'll key off of that, and you'll do the right thing. Or you'll only do the wrong thing once. So this is sort of bad. Now the good news is the pager will never read or write past what it thinks is the end of the paging file. And it will never, so let's say the paging file is 20 meg, we're extending it to 50 meg, we won't do any writes past that 20 meg until that call that extends it returns. So we won't say, oh, let's block all writes until it returns. We'll just continue to do writes in the first 20 meg of the paging file, or reads, until that returns. And we time out that call after a while. We'll just sort of say, okay, let's go do this. If the file system's real busy, after about 20 or 30 seconds, we just say, hey, we're going to give up. The call's still there. It might finish in our lifetime, but we're going to make a best guess. The guy wants a 50 megabyte extension, we're going to say no. If he wants a 5-page extension, we're going to say yes. And so we'll overcommit in the expedient case. The other thing we could have is we could stack multiple extends of the paging file together. Say 4 people all request allocate virtual memory committed at the same time, each one for 10 meg. We'll obviously get one extension for 10 meg, another extension for another 10 meg, etc. As we come through, we'll wait on those sequentially. We won't cancel them or try to combine them. We'll just wait for them. And we'll block everybody. So you can see these very unusual behaviors to your paging file where you get 4 calls right in a row to extend it, and then all of a sudden you can get multiple calls to contract it. And we try to be sane about contracting the paging file. We try not to have it bounce up and down. So typically you see it go like an elevator up, and then it'll quickly come back down, and then go up again and come back down. But I mean, we're talking on 2 or 3 minute increments of shrinkage. It's not, you won't see it that radically. The bad, sort of the last corollary is you have to trust the memory manager to only write within what it's allocated in the paging file. So you can take whatever shortcuts you want to for those page writes because you believe the memory manager. And we won't write past the end of it. Okay, we talked about this flush image section. It's got to be called every time you delete a file. The rule it's got to, or else we won't flush the cache, and you'll have cache coherency problems. In fact, you'll have them big time. Because what will happen is somebody will run Excel and they're wondering why some of their pages are coming from the old EXE and some of the pages are coming from the new EXE. And it's very, very bad. Every time we find this, it takes quite a while to find out where the bug is, whether it's the memory manager, the file system, or cache manager. So we go racing through this and go on a long escapade to find it. The other thing, of course, we find when we're bringing up new hardware architectures, that they have some rules about flushing translation buffers and flushing system caches that we haven't followed. And we think it's the file system, it turns out it's the kernel. The other rule is if it returns false, that means that somebody's got that file open, and even though there's no handle open and exclusive, the memory manager's got that reference, and it wants to enforce its own concept of locking for exclusive, or locking, opening the handle for an access type of exclusive. The other nasty thing we do, and this is for convenience, is when we open files as executables, we open them for delete shared, which says that you can that allows you to rename the file while it's running. Okay, so if anybody was running NT version 3.1 and you wanted to copy a new driver down, what did you do? You renamed the file and then copied your new driver down. But you couldn't copy it on top of it. You couldn't copy it on top of it because the flush image section called returned false. But you could rename the file because we opened it, delete shared. Okay, so we're very nice. Now in NT 3.5, we solved that problem at all. We don't even open the driver files anymore. So now you can really clobber yourself because you can copy new drivers right on top of old drivers, and it just happens. So if you're not running NTFS, if you're running FAT, there's no security on those, so you can actually delete your drivers. If you're running NTFS, we'll put a system apple on it and solve that problem. And the main reason we did that was it saves all those structures, obviously. There's no open handle, so there's no file object. And when you have 10 or 12 drivers that don't have file objects, it adds up to about 8K of memory we saved.
That means you never pay the driver file.
That means we never page from the driver file. And the reason we don't ever page from the driver file when you think about it is we never know where a driver is going to reside in the virtual address space of the system. So we have to do the fix-ups. And as soon as you do the fix-ups, that means you're going to write to the code and to the data, which means that it's probably useless to page from the driver file now anyway because we've modified all the data. And so that's why we take that shortcut. Okay. Rule number 5 is our favorite call, flush image section. Must be called before the file is open for write access. And think of our old excel.exe once again. We want to update block 29 of the Excel file. We'd rather not have somebody running it while we do that. And again, if it returns false, you can't proceed. And the reasons are the same as the previous slide. Rule number 6 is, we just added this in Daytona. This was everybody playing with VC++ version 1.5 and wanting to know why the linker created 2 megabyte files and having to get the new linker. And this is why, because somebody wasn't calling can file be truncated. And the reason they weren't calling it is because it wasn't implemented in the memory manager, so sort of my bug. What happened was, to explain this really terrible problem, is imagine that I have a map file. Let's say it's a 2 megabyte map file, and I'm happily playing on it like the linker does, because our linker actually creates the executable as a memory map file for write, and to make matters even neater, it maps all your libraries and objects as memory map files for read. So you can see that we really like memory map files. And one of the nice things about it is it lets the linker build up the data structures in place without having to do IOs all over the place. Because if you really think about how the linker works, it's got to put out the code sections towards one end of the file and the data sections at one end, the debugger information all the way at the back of the file. So the linker is really moving along through the file. Well, it's better to let the memory manager, in this case, do the file caching than it is to let the file system do it. It's just because in this one thing, it's just so ran that the memory manager can be better. So what would happen is we get this file all the way done, and then we truncate it back to the right size. Okay, so the linker would take a guess and it would say, gee, I wish I had an 8 megabyte file. And it would go do all the work, and then it would say, okay, truncate it back to 612K bytes. Unfortunately, it still had the file map when it did the truncate. So think about it. So the file system says, okay, truncate the file, and it now says, okay, I only know about 612K bytes of that file. That other, 7 megabytes is still sitting in memory, okay, potentially, and the memory manager thinks it's good data, so it's going to flush it out. It's going to do all these other things, but yet the file system doesn't want to have anything to do with that data. So think about the inconsistency. Sometimes you touch a page that's out in that part that wasn't truncated, that 7 megabytes, and sometimes you get the data that was in memory. Other times you go to the file system. Of course, we're reading past the end of the file, so the file system returns status end of file, which we just say, oh, I should give a guy a page of zeros, so we give him some zeros. So sometimes he gets his data, sometimes he gets his zeros, which means that we violated our rule of coherency. The file isn't coherent anymore because you can't tell whether what's in data doesn't match what's in memory doesn't match what's on the disk. So that's how we fixed that. Unfortunately, we broke the linker. The fix to the linker was unmap the view and then called it truncate, and everything was okay. So let's go to the last rule. Rule number 7, and this burned our file system just a couple months ago, is we only check for errors in the memory manager, not warnings. So if you say, warning, I didn't write that data, and it's a severity code in the status, well, too bad, we think you did. So make sure that if you want an error returned, you return an error. And this is very important because it's the file system cache manager that calls flush to actually write those pages. So if you just return a warning saying, yep, I didn't write those pages, and that's because this disk went away or whatever reason, well, too bad. We're going to return back to the file system that, yep, the data's out there, you can count on it. So make sure you get your error levels right. The simplest thing is it's either success or it failed. Be very binary and try not to get into the shades of gray. And that's it. So I'm sure there's a few questions. And you're back on schedule, maybe.
Okay. First question is, can one perform kernel memory allocations on the page fault path?
Yes. You can call EXAllocate pool
Okay.
on page fault path. Non-page pool. You don't want to allocate page pool.
Okay, so it's not. So the answer is no.
Yeah, the answer is yes. You can call on the page fault path. You can call EXAllocate pool.
Okay.
Non-page.
And that's always non-blocking.
Yeah, that's always non-blocking. In fact, remember, it can return null. When you call EXAllocate pool, it can return null saying, hey, there's no pool available. There's another one called EXAllocate pool for non-page must succeed, which says if this allocation doesn't succeed, you might as well just commit suicide because we can't do anything. Okay, so memory manager actually uses that to allocate structures for paging. Obviously, if we can't page, we can't run the system, so we might as well commit suicide. So that you'll get these bug checks when non-page must succeed pool is full, and there's only a few pages of that. So you should only be using it for short time allocations. Okay, you shouldn't say, oh, gee, I'm not going to check my error return status, so I'll always use that.
Okay. Next question is, can the file system tell whether it's being called following a page fault or just being called by the cache manager?
No, the bad news is because everything goes to the same path, that you can't tell who's calling the file system. Okay, you know what file object it is,
Yes.
but you don't know whether it's the cache manager or the memory manager. Now, I'll give you a hint. If it's the paging file, it's always the memory manager.
Well,
Cache manager can never affect the paging file, but for map files, remember, when they're mapped into the system cache, they look just like any map file. We do the I/O the same way. You can't tell the difference.
Okay. And the last question is, how many references on a file are being held by the memory manager?
One. I take that back. One.
Is it one per page or one per client? Or?
It's one per data type mapping. So if I map the file as code and data, it would be 2. But if I just have it mapped as data, it would be 1. And that's because we want to be able to do those closes separately without having to worry about them together.
So when all the references go away, the reference count drops to 0, even though there may be pages in the cache?
No, because we won't, until all the pages go out of the cache, we won't decrement that reference count. So the memory manager keeps the reference count up until every page is left in the system. Okay?
Just a moment ago you said that you're keeping one count for each type of mapping.
Yeah, okay.
So if all the mappings go away, but there are some pages left in physical memory,
Okay.
do I see a reference count of 0, or do I see a reference count that's not 0 on the file?
Here's when the file object is dereferences. When all these things are true, when there's no user map views in the user system cache, there's no section objects, which mean no users have a handle to a section, and there's no physical pages containing any data from that file. And you can think of, people who know NTFS know it has multiple streams. Think of an executable that has code mapped as code, and executable mapped as data. Think of those as 2 separate files.
Right.
Because as far as the memory manager is concerned, they are. So we will, if you open up Excel for both data, for read-write, and you open it as an executable, we'll have, the reference count will be incremented twice, once for the read-write part for the data, once for the code. When all the data pages leave memory, we'll decrement. So when there's no handles, there's no map views, there's no physical pages for the data part, then we'll decrement that handle.
Okay.
Okay? But it's still up because of the code, so that has to have the same thing. No user map views, no references, no pages.
Right.
And that one will go away.
So now there's one reference left for the text.
What was that?
There's one reference left for the code. Right? You said,
Yeah.
okay, now, when does that go away?
When there's no user map views, sections for the code, right? Because you could say map view, remember now, yeah, you probably don't know this. Because it's probably not documented in Win32, but when you create a map view, you get to specify whether it's data or executable that you want the view for. So, and I think the reason you don't know about that is that Loader's the only person who ever maps it as executable, and so there's no need for users to know about that.
All right.
So that's how that second handle gets there. What was that?
Your file system, you don't have to worry about it.
If your file system is the user, you don't get to worry about it. You just get the, in fact, you just see the reference come in. The memory manager hides that all from you. Yes, next question.
My question is again about what's mandatory. Obviously, there at least one file system, the one you're providing, the CDFS, is read-only, so it can't support any of the 7 must rules. How is that taken care of?
It supports all the 7 rules, right? Because it never has dirty data, so it never has to call M, right? You can't delete a file, so it never has to call. But if, right, so it does support the rules.
So is the paging file then only related to those files which are going to be found read from that file system?
Paging files are files that are used, let's see.
Because obviously there's a system cache. And
yeah, paging file is this thing you create to the system's applet that you know, when your system comes up and you say, oh, gee, I got a 60 meg system, I need a 20 meg paging file with a maximum of 40 meg. It's that file. It's where the system pages data, like, for example, data that's can't go to the disk. I can't go to a map file. Let's see, how do we say this right? The virtual memory people all understand this. It's where we swap data to so we can run more physical pages. We can have more data in memory conceptually than there is memory.
So you never try to swap read-only data. Is that?
We would never write read-only data back to the paging file because we know that we can always go and find it in another file on the disk.
Okay.
Okay, so the memory editor tries to minimize what it does write as best as possible, and the hardware usually has mechanisms so we can tell whether a page has been modified or not. And then once that page has been modified, we say, oh, is this tied to a read-write file? And if it is, we'll write it back to the read-write file. But if it's not, if it's tied to a read-only file, like an executable, then we write it to a data file, excuse me, the paging file. And that has to do, the other trick with that is if you look at the page protections when you allocate virtual memory, excuse me, when you create file mappings, one of them is page write copy, which says that as soon as I write this data, I want a private copy, and when you throw it out of memory, throw it to the paging file, not to the main file. And this lets databases do some pretty clever things. I don't want to get into that now.
Before we leave your original question about what should you implement and what shouldn't you implement, I spent some time talking to Brian after his talk, and it's interesting to recognize that CDFS implements OpBlocks, for example. CDFS implements all the directory change notify APIs. CDFS implements all of these things. The reason CDFS implements all of these things, and Lou is advising you to implement all of this stuff, is that it presents a consistent view of the file systems to all users. So an application, some dumb application that comes from, you know, some vendor out there, none of the people in this room, of course, which doesn't recognize that, in fact, it's speaking to a CD file system or it's speaking to a remote file system, will continue to work consistently across all the file systems. So if you look in CFS, you'll be surprised to find that it in fact implements OpBlocks. It in fact implements directory notifies. It even, you know, things like rename, which it obviously will never happen in CDFS. Things like that. So the code examples for the kind of things, the kind of interfaces that need to be exported by file system are all there in CDFS. So if you look at what CDFS does in terms of what it implements and what kind of things it supports, with the exception of the paging file, of course, then you'll see that that's the interface that we think people ought to be exporting from a file system. Because CDFS, even though there's a lot of things it could punt on, we've taken the extra time and put the extra work into making CDFS understand these APIs and export meaningful responses to them. Okay?
There's another important point there. You said, which things in memory management don't I have to implement? The answer is you have to implement them all. However, there's one caveat. If you never let a paging file be created, you'll never have any paging I/O go to your file system. And remember, it's a special call to come and say, create me a 20 megabyte paging file. If you return, can't do it, you're never going to get any paging I/O to your file system. And this is what the redirector does to prevent you from putting paging files on the network. Even though that would be a very convenient thing to do, it has some problems in that you can block in times when you don't want to block. So that's why the redirector will let you do that.
Can it trust all device driver BDM protocols, etc., to have these IRPs that are on behalf of paging protocols?
The question is, can I trust all the device drivers below me to handle the IRPs for paging files appropriately? And the answer is you have to, but more importantly is, the good news is typically sitting below the file systems at the paging level is merely device drivers, disk drivers, or fault-tolerant drivers. So you're talking at a very low level. And it's typically the layers above the file system that may block more, like a distributed file system or something that's doing some fault tolerance type of things.
If I wanted to implement NFS, better not trust UDP to be non-blocking, for example.
Right, the question is, if I implement NFS, should I trust UDP to be non-blocking? And I would suggest not having a paging file over NFS until your file system is relatively mature and you really understand the characteristics. Because obviously, when you think about it, if you have a paging, here's the downside. Put a paging file on a remote device, and that network connection goes away, your system's no longer functional. Because there's probably some important data we have that we can no longer get, which means the user's going to get an in-page error. But of course, very few applications know how to deal with in-page errors. You went to run some code, the code couldn't be paged in, we pop up an error, and so you get this little pop-up. There's nothing you can do at this point. In fact, it may be the code that put the pop-up up is sitting on the paging file, in which case the system just sort of hangs. So we haven't felt comfortable putting stuff on remote devices yet. Now, as the networks start getting better and better with some of the new devices coming out, we'll probably start doing that. It makes a lot of sense because it lets you take a large disk of a lot of paging files on there. It really lets you distribute some stuff off your small workstation. Again, going towards a diskless workstation type environment, which a lot of people would like. Right here.
Can you upgrade and downgrade protection on pages? For example, if user maps a file and they want rewrite access, can the file system in the memory manager conspire to only provide read access so that you actually get a paging request in and out?
Yeah. The question is, can you upgrade and downgrade protection on individual pages so you can control what you get? And the answer is there's mechanisms to change the protection of a page, of a memory map file, so you can make it no access, read only, read write, copy on write, or execute only. Now, the hardware we have right now doesn't support execute only, with the exception of Alpha that could have, but DEC did decide to expose that in their microcode, in their PAL code. So there's no implementations that do execute-only protection, which probably means most apps would be able to turn it on.
But the answer is yes?
But the answer is yes. So you can actually, as a user, you can say this page is read-only, and you'll never get a write to it.
Well, I'm asking the other question. If a user maps it read-write, can the memory manager and the file system, the reason you want to do this is like network shared memory, where you don't want the memory manager doing network coherent shared memory protocols. You want the file system read-writer to do it.
Right. The question is for network coherent protocols, can you stop the user from doing the writes by marking it as read-only? And the answer is no. You can't stop the user from doing anything he wants to, which is the unfortunate thing. The user's going to say it's read-write. If the file is open read-write, we're going to let it go. The one thing we don't promise is that if you open a memory map file over a network, we're not going to try to keep it coherent between the machines. Okay, there's no in the distributed lock package or anything like that to say, well, I have this data on this machine and it's been modified, so I better not let it go over on that machine and be modified. What happens is each unique machine will do a page fault to that data, write to it, know it's dirty on that page, but they have no idea anybody else has that. And that's, a future research project to make that all work. The bandwidth right now isn't high enough for us to even consider doing that, but we know people want to do that. At the microphone?
Yeah, this is something related to the question that was just asked, and something that I asked the gentleman who gave a talk on the cache manager yesterday. Is there any way that I can force pages to be discarded from the memory subsystem if a user's mapped a file in, or if an executable is running?
You can't force a user to discard pages. And the reason, the real simple reason being is we have no back pointers from the physical mapping of those pages to what users have them. Okay, we only have the pointers from the user's address space to where the stuff is on the disk, but we can't go and find all the users that have a page. Because remember, like 15 processes could all map the same file, all have different protections, etc. And we can't keep all the links to go to all 15 processes.
That's right, but what you do have is you do treat the virtual address descriptors that you have for a process. A user is allowed to request memory that's not committed. You have certain structures that you use to have, if multiple users are sharing the same page, you have a common structure that you have those users' virtual address descriptors point to, and then that structure references the page, the physical page in memory, and you have a back pointer to that common structure.
I have no back pointer.
Okay.
You're missing. There's no back pointer. We debated putting the back pointers in, and the problem is it just adds more memory, and we're trying to become a little bit smaller.
Right. Well, just now you just said that there was no policy for maintaining coherency across different machines, but for file systems, network file systems, effectively, is it true then that if you have a user mapping a file in on one client and some other user, for example, to a database, wants to read-write same file on some other client, you have forced every single user on the first machine to get stale data?
That's right, and it's the database's problem for letting that file be opened, right, because it didn't do an exclusive open when it first opened it, and the database is not managing its data properly. We provide all the mechanisms for the databases to prevent this from happening. It's up to the application to make sure it implements its calls properly so it doesn't get burned by this.
Right. Well, we have a file system that's distributed in nature, and we do all the coherency management ourselves. The problem is that NT has now effectively precluded a distributed shared memory implementation to exist with NT machines in that environment. Is that true?
The current way it's designed, it doesn't provide the notification you